Okay, hi folks. We didn't have time for our Charles Law Lab, so we will just go over that today a little bit. So for the Charles Law Lab, your objective will be to extrapolate some data to estimate absolute zero in Celsius. Okay, so here's basically how the Charles Law video works. You first take one of these micro pipettes that we used for Boyle's Law as well. You fill it all the way full, and you count how many drops it takes to empty it. Drop, 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 how many drops to empty it. In the case of the micro pipette we used to get this data, it took 160 drops to empty the pipette all the way. And you want to do that a couple of times, make sure it's really 160 and you didn't lose count. But so I did that carefully, and we got 160 drops from one of these pipettes. You want to make sure when you're dropping that you are straight up and down, so that your drop size is even, right? If you're kind of crooked, the angle change can affect your drop size, so you have to be careful about that. So that would be water volume. At 0 Celsius, 160 drops of water fit in the pipette. Okay, so then to collect the data, what you do is you would put your micro pipette in varying temperatures of water. Okay, so the coldest temperature I used was 21 Celsius, right? So I basically took some water out of my ice bath, let it come up, maybe to kind of 21 Celsius, put it in something so that the whole bulb of the micropipette was underwater, right? So that and it's able to flow in and out, right? So the gas can flow in and out. So we heat up the air with the surrounding liquid. So the air in the bulb hopefully came up to 21 Celsius because the bulb was submerged. So then I would just grab and pinch it shut with the tweezers here, and then I would submerge it under ice water, all the way under ice water, and let it go. And so once I let it go, because the air in the bulb was able to expand, because this was a little warmer than ice water, and then I closed it off, put it under ice water, then it will contract again, and it will actually suck up just as much water as the amount of gas that flowed out, because it got warm and the gas expanded, right? So then I dropper, drip, 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 drip. How many drops got sucked up when it went in the ice water, and the air that had expanded when it was warm then contracted when it got cold again. And I found that at 21 Celsius, it got 8 drops of water into the pipette when it submerged. So then I just continue here heating it up. So I had just heated it up a little at a time, 30 degrees, 40, 50, and then it started to get a little more difficult, 57, 65, 74. And then the last trial I did was 88 degrees Celsius. And at 88 degrees Celsius, it essentially started melting my little pipette. So my plan was, I got 88. I want something between them. But when I got my data for 88 Celsius, which is, getting close to the boiling point of water, and it made this little guy fail. So then when I let it cool off and tried to get a data point for 81 degrees Celsius, I found that the pipette had melted so much that I couldn't get a data point. So I tried, but it did not work. So basically what happened is the warmer the liquid that was surrounding the pipette when it was empty and able to allow gas to expand, right? As we got hotter and hotter, then more and more drops, once I grabbed it here, and moved it under the ice water, I would suck up more and more of that cold water because it had expanded, and then that contracted and let it suck up some water. So We started with 160 drops in a cold pipette, and each time I did the experiment with warmer temperatures, it sucked up more and more drops. So I added them together, right? So the 160 drops at 21 Celsius plus the 8 drops is 168. The 160 drops plus, say, the 38 drops I got at 88 Celsius is 198 drops, right? So we can see here the data that you're going to need to graph. When you make the graph, and I'll attach a copy of my graph so you have an example, you can do it on your calculator, you can draw it by hand on graph paper. You want to leave room to be able to extrapolate down to absolute zero. So you're going to graph the temperature on the x-axis. You're going to graph the total volume in drops on the y-axis. I use Desmos to make my graph. It's a free app. Did it on my phone even. It has also a website that you can use for free. You could use Microsoft Excel or Google, what would that be? Sheets, I think, is their, or their Excel-like document. But anyway, I extrapolated my data. So you can see the range of data that I collected was from 0 Celsius to 88 Celsius. I extrapolated all the way down to see where it would cross the x-axis, and it crossed for me about negative 275 Celsius. Now that's great because we know absolute zero is negative 273.15 Celsius, so we got extremely close. And I'll attach my graph with my best fit line drawn on. It's pretty faint. The best fit line was faint on my phone, but hopefully you can see it. And then, were you comfortable? We discussed, of course, with Boyle's law, how far can we extrapolate? And I said, no, I'm not comfortable extrapolating to negative 275 Celsius when my data range was only 88 degrees. I would be comfortable extrapolating within plus or minus 10 degrees of my data, right? So about 9 degrees Celsius below zero, or 88 plus 9, what would that be? Goodness, I'm tired at the end of the day. 88 plus 9 is 97 degrees Celsius would be as far as I'd be willing to extrapolate. I think 10% is a pretty good range for extrapolating, but beyond that, and especially far beyond that, is bad science. So go ahead and take a look at my graph. Please create your own, record this data in the chart, and hopefully that helps you to see one way that absolute zero could be estimated with really low tech supplies. So there we go.